thank you for attending this seminar, which will be held in English because there are people attending from everywhere, and it will be also recorded and then made available on our channel. I am Marco Baldi. I'm an associate professor of telecommunications at Marco Baldi University, and I am pleased to coordinate this PQ Cifris initiative, which is an initiative inside the big container of the Italian association, the Cifris, for cryptologic research. We are a working group inside the Cifris working on post-quantum cryptography. And among other things, we are organizing some seminars from time to time for speaking about recent advances in post-quantum cryptography. As you know, this area is playing a more and more important role in these years. There's an important ongoing standardization by NIST. There are many research groups who are focusing on this area of research. And so we try to keep interested people up to date and to provide an overview of the most interesting advances in this area. Now, before the end of 2021, we are organizing two seminars. The first one will be today by Paolo Santini, and the second one will be on the 7th of December by Cecilia Boschini. These two seminars concern two important aspects of post-quantum cryptographic research. Today, Paolo will speak about code-based cryptography. That is one of the main areas, one of the main lines of research inside post-quantum cryptography. While next month, Cecilia will speak about digital signatures, and in particular about some leakages during the verification of digital signatures. Well, coming to today's talk, Paolo Santini is a young researcher working at Marco Baldi University. He's working on code-based cryptography since several years, and he was also one of the proposers of the LDPC suite of post-quantum asymmetric algorithms. And today, Paolo will speak us about recent advances in code-based encryption and digital signatures, focusing on code-based cryptography, that is cryptography using error correcting codes. So thank you everybody again. We will then make the recording of this seminar as well as the slides available through our websites. And please don't hesitate to ask questions if you have, both during the talk and especially after the talk. Paolo will remain connected for answering your questions. Okay, I believe that's all. Thank you again, everybody. And Paolo, the stage is yours.
Okay, perfect. Thank you, Marco, for the nice introduction. Okay, so good afternoon, everybody, and thank you for being here. So my name is Paolo Santini, and as Marco said, in this talk, I am going to speak about code-based cryptography. In particular, I will focus on two applications, that is that of encryption and that of digital signatures. The idea of this talk is that of giving you a high-level overview of the status about code-based cryptography. And also, I would like to give you some ideas for what may happen in the future of this research area. Okay, so let's start. So, as we have said, we are speaking about code-based cryptography. And at the moment, essentially, everyone knows that code-based cryptography is one type of post-quantum crypto. First of all, do we need post-quantum cryptography? Well, the answer is probably yes. Indeed, it is known that several experts in the area believe that quantum computers will become real in the near future. So this means that in a decade or maybe 20 years, there will be quantum computers that will be available. And this means that these computers can be used to essentially break all of the public key cryptography we are using nowadays. It is indeed well known that, first of all, quantum computers can do things that classical computers cannot do. And for instance, if we consider Shor's algorithm, then we know that we can break schemes such as RSA or El-Gamal in polynomial time. Note that having an attack in polynomial time is something that is really a bad thing, we can say, because essentially this means that we cannot simply increase the parameters of the scheme. So if there is an attack that runs in polynomial time, this means that if we want to achieve practical security levels, then we need very, very huge public keys. So the scheme will not be practical. So this is a very big problem, because this means that if we want to use public key cryptography, then we need new mathematical problems. So we need to change completely the type of algorithms that we are using. And this is why we speak of postquantum cryptography. A scheme that is post-quantum must be secure even when we consider attacks implemented on quantum computers. As a major evidence of the importance of post-quantum cryptography, we can mention the NIST standardization process. Consider that some years ago, probably in 2017, if I'm not wrong, NIST started this process for producing a new standard containing recommendations for post-quantum cryptographic primitives. In particular, the process has been organized as a sort of competition divided into rounds. In each round, the NIST itself and the community evaluates candidates, and at the end of each round, some candidates are eliminated according to recent results, attacks, these kind of things. The competition started with 69 submissions in the first round, and right now we are in the third round and we have only 15 candidates. In particular, the candidates have been divided between finalists and alternates. The finalists are the algorithms that are ready and that will probably be standardized at the end of the competition, while the alternate candidates will probably be kept under evaluation for another additional round. So I promised to you that I'm going to speak about code-based cryptography. So let's have a look at code-based crypto in the competition. In particular, in the third round, we have three primitives. We have the classic McEliece that is among the finalists. So this scheme is going to be standardized probably pretty soon, while Bike and HQC are included among the alternates. So we see that 3 out of 15 algorithms are based on codes. So this means that code-based cryptography has become very important and is now considered among the most secure things that we have at the moment. So we can say that it offers very strong security guarantees and also pretty good performances. So I mean, this is a major evidence that code-based crypto is indeed important and it is becoming real. So let's start. We are speaking about code-based cryptography. So clearly the basic ingredient is that of linear codes. So let me give you some notation. We are considering only linear codes. We have that FQ is the finite field with Q elements. And we say that a linear code is a code with length n and dimension k if it is a linear k-dimensional subspace of the whole space FQ to the n. Some important parameters, we have the code length, the code dimension, the code redundancy, that is the difference between n and k, and the code rate, that is the ratio between k and n. So this can be considered as a graphical representation of a code. We have the whole space, FQ to the n, we select only a subset of the vectors. You see this gray set, and these code words constitute our code. In particular, if we want to have a compact representation, we can use two matrices. So we have the generator G or the parity check H. G is a basis for the code, while H is a basis for the null space of the code. Finally, consider that normally codes are studied under some metric. That is, we use a distance function that is used to somehow measure the distance between code words. In this case, in this talk, we are going to focus on the Hamming metric, that is probably the simplest one, which is defined in the following way. If we have a vector A, then its Hamming weight corresponds to the number of coordinates which are different from 0. Okay, so when we work in cryptography, we need hard problems. And the standard problem for code-based crypto is normally called SDP, Syndrome Decoding Problem, which reads as follows. We are given an arbitrary parity-check matrix H and a syndrome S, and we want to find a vector E such that the product between H and E is equal to S. In particular, we want this vector to have low weight. So we consider another input T, which is deemed as the upper bound on the weight of the solution. Consider that the weight requirement is very important because it is what makes the problem hard. Indeed, we have a very important result that states that the SDP is NP-hard. So basically, SDP is among the hardest problem that we can think of. In particular, to have an idea about the actual hardness of the problem, we can consider the complexity for the case of Q equal to 2. So we are considering the binary case. In this case, the best solvers are known as information set decoding, ISD, and the running time is a function which has this form here. And you see that the complexity is exponential in the number of errors. If we consider the quantum version of ISD, we have that we can actually obtain a quadratic speedup if we embed Grover's algorithm into ISD. By doing this, the exponent gets divided by 2, but it still remains exponential. So roughly, we can say that this expression is the reason why code-based crypto is post-quantum, because even if we consider quantum attacks, the complexity, the running time is exponential. Okay, just one, let me point out that actually we can have several variants of SDP, so we can change the problem. And this the actual hardness of the problem depends on the requirements that we are considering. For instance, we can also consider different metrics, such as the rank metric or daily metric, and also different constraints. For instance, we can require the solution to have a very high weight. These are other solutions. But in this talk, I'm going to stick to this definition. So we consider the case of very low Hamming weight, because it is the most studied one. So it is also the problem for which we have the maximum amount of literature. So we have a pretty good understanding of what happens when we consider such a problem. Okay, so the first ingredient that we need to obtain a crypto system is an hard problem. And we have seen how an hard problem can be obtained. Now we need a class of codes for which SDP can be easily solved. And this class of codes is that of error correcting codes. Consider that a standard application of codes is that of correcting errors over noisy channels, which means that assume that you want to send a code word over a channel. However, your channel is not good. It behaves in a bad way, so that instead of receiving C, you receive X, that is the sum between C and D. E is the error vector introduced by the channel. If a code is an error correcting code, then it admits a decoder. That is an efficient technique that allows you to find the E. So basically what a decoder does is taking X as input and estimating E and computing X minus E. Okay, clearly the decoder must be efficient, so it must run in polynomial time. In any case, the important thing is that a decoder, for an error correcting code, we have an easy way to solve SDP. So if we put the hardness of SDP together with the existence of error correcting codes, we see that we have an intuitive way to construct a trapdoor. And you can consider this general framework. We pick an error correcting code, and it is our secret key. To obtain the public key, we map the code into some random looking code C prime. If we want to encrypt, then we just pick a code word of the public code and we add an error vector. So this is our ciphertext. When we want to decrypt, sorry, it is enough to first demap the public code into the secret code so that we can express the ciphertext as the sum between a code word of the secret code and an error term. And once we have done this, it is enough to run our decoder. We retrieve the error term and we find the initially transmitted code word. Consider that this works because an opponent has no, this works if an opponent has no way to guess C from C prime. So in the end, what an opponent sees is only the public code, which looks like a random code. So the adversary has no way to rely on efficient decoders, and the only thing he can do is relying on ISD. So this is the basic framework to obtain code-based encryption scheme. In particular, code-based cryptography has been initiated by McEliece in 1978 with the first paper about code-based cryptography. And this is why the scheme is called the McEliece cryptosystem. And so the McEliece cryptosystem is basically based on this framework. Okay. Now, I won't enter into the details of the scheme. For us, it is enough to know that irreducible Goppa codes were used. Goppa codes are algebraic codes, so they are constructed starting from some properties about polynomials. We know that they have an efficient decoder, for instance, the Patterson algorithm. And in particular, let's see how the public code can be obtained. So we have that our secret code, our secret key is G, that is the generator of the secret code, while the public code is obtained as G prime equal to SGP, where S is a random change of basis, a scrambling matrix, and P is a permutation, a random permutation. So in the end, the effect is that C prime is undistinguishable from a random code, which means that by looking at G prime, an adversary has no efficient way to obtain information about G. So if this property holds, then the adversary cannot rely on some efficient decoding technique and must use ISD. So this is how we obtain our trapdoor. Okay, so the good aspects of the McEliece cryptosystem are, for instance, its efficiency, because the scheme is pretty fast, but most importantly, its security. Indeed, the McEliece cryptosystem is 43 years old, but at the moment we have no known cryptanalysis, which means that there is no efficient way to retrieve the secret Goppa code from the public code. So we have a pretty good confidence about its security. Okay, there exist some cases where we have some doubts, because, for instance, if you take very high-grade Goppa codes, then you have a distinguisher. So this means that there can exist some attack. But in any case, if your parameters are properly chosen, then you have no way to attack the schema. However, and this is a very big however, the scheme is also known because of its very large public keys. To make an example, if we want to reach 128 bits of security, that is the standard security level we use nowadays, then we need public keys of 260 kilobytes. It is quite a lot. I mean, we cannot say that the keys, the public keys of this scheme are compact. So this is why along the years, many people, many researchers have tried to reduce the public key size of the McEliece crypto system. The common idea has been that of replacing Goppa codes with other families of codes, hoping to obtain some reduction in the key size. We have seen, for instance, schemes based on generalized Solomon codes or subcodes of these codes. We have seen other types of solutions, for instance, those based on quasi-dyadic, quasi-cyclicity, convolutional codes. However, consider that we cannot say all of them, but almost all of these proposals have been cryptanalyzed. And the problem is that when you apply too much structure on the secret code, then you are essentially revealing too much information about the secret code, so that when you compute the public code contains information about the secret code. So in the end, if you try to improve Goppa codes with using other types of algebraic codes, then you have to be very careful, because attacks may exist. However, very secure solutions exist if you do something that is completely different. And this is the case of quasi-cyclic LDPC and quasi-cyclic MDPC codes. Consider that these two types of crypto systems nowadays are the ones with the smallest keys. And they are also, they have appeared in the NIST competition. So I am going to focus on these two families of codes, because they can achieve very compact keys with respect to the original proposal based on Goppa codes. Okay, so I'm speaking about LDPC codes, that is the acronym of Low-Density Parity-Check. This type of codes have been invented by Gallagher in 1962, and they are nowadays employed in several standards. So we know quite a lot about LDPC codes. To understand how an LDPC works, we can consider a graphical representation. So we define the Tanner graph, that is a graph containing two sets of nodes. We have n variable nodes and r check nodes. And we have an edge between a variable node and a check node if and only if the corresponding entry in the parity-check matrix is set to 1. Now, to understand what happens when we consider an LDPC code, we can start from the Tanner graph of a parity-check matrix defined in this way. You see that the corresponding Tanner graph is complete in the sense that it contains the maximum number of edges, and the parity-check matrix contains the maximum number of set entries. Now we start including some zeros. So for each row, we replace some ones with some zeros. You see that while we do this process, the number of edges in the Tanner graph reduces. Okay, so you can see that we started from all the possible edges, and now we have only a few of them. Clearly, this is an example, but if you consider a very large parity-check matrix with a very small number of ones of set entries, then you end up with a graph that contains a huge amount of nodes and a very small number of edges. So this is the property that defines LDPC codes. An LDPC code has a parity-check matrix that contains a very small number of set entries, and this corresponds to the fact that its Tanner graph representation is a sparse graph, in the sense that it is a graph with a very small number of edges, which can, I mean, in different words, every node in the graph has a low degree. Now, this property is fundamental because it allows for the design of efficient decoders. In particular, decoders for LDPC codes are message passing algorithms, which at a high level work in this way. So we have a first phase, which you can see as some preparation for the decoding, where the variable nodes are initialized with the values that are received from the channel. So some of these bits will be equal to the code word bits, while some other bits will be different, and these bits will be those affected by errors. Then decoding can be seen as a two-phase procedure where the nodes exchange information. So in step one, variable nodes send their values to the check nodes. The check nodes run some computation, and then they reply with some kind of information. So we have these two steps. And in particular, efficient decoders for LDPC codes are iterative in the sense that these two steps are repeated. And in particular, the iterations go on until the nodes reach consensus. In that case, we have a decoding success. So the graph has estimated the transmitted code word. Or decoding may stop when the maximum number of iterations is reached. In that case, this means that the decoding has failed, and so we have a decoding failure. In particular, we see that since the complexity can be estimated on the number of messages that the nodes exchange, since the graph is sparse, then decoding is very efficient. Okay, so this is a very high-level overview of how an LDPC decoder works. Now, I told you that we have some failure probability, which we normally call DFR, the decoding failure rate. And normally, this probability is estimated through numerical simulations. So we implement the code, we implement the decoder, and we run experiments to see the probability with which decoding fails. So if we do this and we let the code length change, then we obtain a graph like the one you are seeing in the slide. So we have this region where the DFR decays exponentially in the code length. This is normally called waterfall. However, we have to be very careful because at some point we have this region, which is called floor, when the DFR becomes polynomial in the code length. So you see that the actual behavior of the DFR is this one, okay? So that if the code works in the floor region, then it is, we can say, bad in the sense that increases in the code length bring very small variations to the DFR. One important thing is that the existence of the DFR is something that is typical of LDPC codes because algebraic codes don't have these issues. So we have theorems proving that algebraic codes can correct an amount of errors, and we don't have such a thing for LDPC codes. And remember this fact because it will be very important. Okay, in particular, in code-based cryptosystems, we normally rely on the bit flipping decoder because of its simplicity. Indeed, it can be shown that it runs in time which is linear in n. It is very easy to be implemented, and it can also be easily parallelized. So in the end, the bit flipping is a very fast decoder. So if we use the bit flipping into a code-based cryptosystem, then we have a very fast decryption. Okay, so in particular, in code-based cryptography, we rely on QCLDPC codes. Let me try to be very fast about this. So a quasi-cyclic code is a code that is invariant under quasi-cyclic shifts. So we start from a code word, we apply a quasi-cyclic shift, and we obtain another code word. A good aspect of quasi-cyclic codes is that they can be represented by circulant blocks, so that we have a matrix, for instance, a parity-check matrix having this form. And you see that all the rows of the matrix are obtained by applying a quasi-cyclic shift to the previous row. So that if we want to represent the matrix, we only need, for instance, the first row. So we have a code, a matrix, but to represent the matrix, we need only the first row. So the storage size is linear in n, and this is why using quasi-cyclic codes, we can aim to obtain reductions in the key size. Okay, so we have defined QCLDPC codes, so we can see how we can obtain a crypto system based on QCLDPC codes. We consider a general framework. So we start from a secret key that is the parity-check matrix of our QCLDPC code. The public key is the systematic generator matrix, which is computed in this way. When to encrypt, it is enough to compute a code word of the public code, and we corrupt it with some error vector E of weighted T. While to decrypt, we run the bit flipping decoder on X on the ciphertext, and we retrieve the code word and the error term. In particular, in this case, we have that the secret code and the public code are the same, but since this matrix here is dense, then the generator matrix is dense as well. And this is where the trapdoor lies. Indeed, I told you that if you want to decode an LDPC code, then you need to know a sparse representation for the code. So you need a sparse parity-check matrix. However, in this case, the generator matrix is dense, so you cannot have access to a sparse representation, so that you cannot run efficient decoders, and then you have to, again, use ISD. Okay, so let me speak a bit about the actual security of the scheme. First of all, we are using quasi-cyclic codes, so we are considering a specific class of codes. In this case, we don't have a formal proof about the MP hardness of the problem. We know that we can obtain some speed up to ISD by using well-known techniques, such as decoding one out of many. However, we can receive only a polynomial speed up, which is also pretty small. So in the end, the community, we have that the community believes that SDP against quasi-cyclic codes is essentially as hard as SDP over non-quasi-cyclic codes. We have also attacks where we use ISD to search for rows of H of the secret key. And we can do this because the rows of the parity-check matrix corresponds to low-weight code words in the dual code. Again, the complexity has this form. So you see that the complexity depends on the column weight V. So if we want to achieve security against this type of attacks, we need to choose V large enough, where V is the weight of each column in the secret key. So now we have that something fun is happening because we started from LDPC codes. So we started from codes where we want the parity-check matrix to be sparse, but we need such matrices to be in some way, because we must resist against ISD attacks. This is why in crypto normally we speak of MDPC codes. That is codes where the column weight grows as the square root of n, and this is done in order to resist against ISD-based attacks. Okay, consider that the term MDPC became famous after 2013, after the proposal of the so-called MDPC McEliece. However, the truth is that people have been using MDPC codes in crypto since 2007, but were called LDPC. So we can say is a bit strange. In any case, the fact is that you can use the name that you prefer. So it can be MDPC, LDPC, whatever. But in the end, you are speaking about the same family of codes. Indeed, LDPC and MDPC have the very same properties. So same decoders, same process, same cons. So call them whatever the way that you prefer, but an MDPC is an LDPC in the end. Okay, in particular, in the NIST contest, there have been 2 proposals based on QCLDPC codes. I'm speaking about LedaCrypt and Bike. LedaCrypt survived up to the 2nd round, but then was eliminated in the 3rd round, while Bike is currently participating in the 3rd round as an alternate candidate. Actually, these two schemes are very similar, so they have pretty strong analogies. In particular, they have the so-called DFR issue, which I'm going to present to you in the following. However, LedaCrypt has also the so-called problem of weak keys, which has been the reason of its elimination. So let me speak a bit about LedaCrypt. In particular, this is a proposal where I was also an author together with Marco Baldi, Alessandro Barenghi, Franco Chiaraluce, and Gerardo Pelosi. So this is the LedaCrypt team. The peculiarity of LedaCrypt is that we chose to generate the secret key H as the product between 2 matrices H prime and Q. We want H to have density square root of n, so that H prime and Q have this type of density. So you see that basically we are obtaining an MDPC code, the Parity-Check matrix of an MDPC code, taking the product of 2 very sparse matrices. The reason of this is that it can be proven that because of this structure we obtain reductions in the running time of the decoder, so that the bit flipping for matrices of this type is faster. However, this is a problem because the presence of this structure gives the possibility to have efficient attacks, in the sense that it can be shown that some types of keys are weak. Weak means that they can be found with very efficient techniques. In particular, it's not only a problem of weak keys. I mean, yes, it is a problem of weak keys, but we can distinguish between ultra weak keys, that are keys that are very, very weak and can be found with a very low complexity. But starting from this type of keys, we see that there is a continuum of progressively less weak keys, in the sense that there are keys where ISD becomes really, really fast. There are other types of keys where ISD has the standard complexity, but between the 2 of them, we have several types of keys where attacks are start from easy and gradually become, we can say, standard. However, the problem is that ISD is never harder than it is for purely random QCLDPC codes. So in some sense, we can say that attacking LedaCrypt is easier. Actually, the attack can be easily avoided. Indeed, the LedaCrypt team, so we propose to choose the Q matrix equal to the identity to avoid this type of issue. However, the NIST team consider this tweak as a major modification with respect to the proposal that we submitted initially. So in the end, LedaCrypt was eliminated from the competition. Okay, so actually, I know this attack pretty well because I was one of the authors of the attack. So in the end, we can say that I killed my creation. Okay. Actually, the attack is okay. It's complicated because this paper is 40 pages long, more or less. So I cannot enter into full details, but I just would like to give you a flavor of the attack. So Consider that if you want to use ISD to attack an NDPC-based crypto system, then what you do is that you guess positions in the secret key, hoping to select only positions where there are zeros. However, remember that in LedaCrypt, we have this particular structure for the secret key, which you can see represented in this toy example. So what happens is that ultra-weak keys are those keys for which all of these polynomials have degree which is not larger than p divided by 4. It is very easy to see that if all of these polynomials have degree which is not larger than p over 4, then their product will give rise to polynomials with degree not greater than p over 2. And if we sum two such polynomials, then again the maximum degree will not change. So in the end, starting from this configuration, we obtain keys, we obtain polynomials, sorry, where we know for sure where we can find polynomials. So in this portion here, where we can find zeros, sorry. We can estimate the probability to pick an ultra-weak key. And we see that, okay, these are the computations. You can trust these numbers. And you see that this probability is larger than this one. So the probability to pick an ultra-weak key is not negligible. And this means that with some probability, that is this one, we have an attack that finds keys in a very efficient way. Okay, so this goes only for ultra-weak keys. Then you can consider different constraints, and you see that the set positions in the polynomials mix in a different way, but still you have some, let's say, some ways to speed up ISD. So in the end, this means that the message is that if in crypto you do things with too many structures, then you may end up in having some security issues. Okay, so this is, again, this attack can be easily avoided if you choose Q equal to the identity. So if you do this, you have that this parity-check matrix is the actual parity-check matrix of a QCLDPC code, and you have what people call pure QCLDPC code. So basically, this is what Bike is doing. However, Bike has another important problem, that is that of reaction attacks. Indeed, I told you that QCLDPC codes have a non-null DFR, a non-null decoding failure rate. And this gives the possibility to mount attacks that are based on decoding failures. Indeed, what happens is that we know that the decoder can fail. And the failure depends on the relation between the error vector and the secret key. So in an INCCA2 scenario, where an adversary sends ciphertext to the decryption algorithm, then what happens is that every decoding failure leaks information about the secret key. So an adversary can wait until a sufficient number of decoding failures happen, and then he can run a statistical analysis to recover the secret key. This type of attacks is rather recent. They have been presented in 2016 and are normally called reaction attacks. And they are actually able to completely find the secret key. So at the moment, reaction attacks are the most dramatic attacks against these types of crypto systems. In particular, if you want to counter reaction attacks, you have two possibilities. The first one is that of using ephemeral keys, but you only obtain in CPA security. Or if you want to reach INCCA2 security, that is the highest security notion, then you need to have a negligible DFR, meaning that you want your DFR to be not larger than 2 to the minus lambda, where lambda is the security parameter. However, having a prediction on the DFR is rather difficult. Indeed, we don't know closed form formula to estimate the DFR. If we want to obtain such a formula, we need additional assumptions. But you know, when you are trying to produce a security proof using assumptions is not a good thing in the end, because this means that you don't dispose of a formal proof for your security. And in particular, another important problem is that we cannot rely on theoretical models, but we also cannot rely on numerical simulations, because we are only able to simulate up to 10 to the minus 9, something like this, while 2 to the minus lambda is much smaller than 10 to the minus 9. So we have this problem. We need a very small DFR, but we don't know how to estimate the DFR. The fact is that, okay, so we don't know how to estimate the DFR. Maybe we are not able to do these computations. I mean, this is always a possibility, but actually, and more probably, the fact is that estimating the DFR is intrinsically hard. Indeed, what happens is that the very small DFR values are due to the so-called trapping sets. Consider that a trapping set is a vector with small weight, such that the decoder gets trapped in some bad configuration. So in the end, a trapping set is constituted by a small number of positions that, however, are able to somehow make decoding very bad, so that with high probability decoding fails. We may try to enumerate the trapping sets, and we may try to compute the probability that the input vector selects at least a trapping set. However, estimating trapping sets is an NP-hard problem. And in particular, we have techniques that can somehow estimate the number of trapping sets, but these techniques depend on the density of the parity-check matrix. So if we apply these techniques to MDPC codes, then the complexity explodes. So, I mean, you see that the problem is indeed hard, because we are trying to enumerate something that, however, is NP-hard. So you see that it is not, it makes sense that the problem is not easy. However, what we can do is that we can find bounds, upper bounds for the DFR. In particular, at the moment, if we don't want to use additional assumptions, then we have models only for one decoding iteration. And in particular, this line of research has been started by Tilish in 2018. Then we worked a bit on it, so that we improved the work of Tilish by basically improving this bound, and also by providing an upper bound which takes into account the probability of failure. We have computed some parameters using our estimates, so that you see that even if we are considering only one iteration, we are still obtaining reductions in the key size with respect to the original McEliece proposal. However, these keys are, I mean, they are not small, they are still very large. So this is, we can say, a strange problem, because we have a decoder. We know that the decoder can perform way better than what we are estimating right now, but we don't know how to prove its performances. So this is really a very strange problem. In particular, at the moment, the smallest keys can be obtained if with the so-called extrapolation technique. That is the one used in bike. This technique is very easy. What you do is that you simulate your decoder up to the best you can achieve. Then you extrapolate the DFR curve, assuming that it is exponential in the code length. And then you use your extrapolated curve to estimate the DFR. Clearly, the good aspect is that there is no bound on the number of iterations that you consider. And you can indeed obtain very compact keys. Indeed, if we take the parameters of bike, we have that to reach 128 bits of INCCA2 security, so the highest security notion. Bike has keys, public keys of only 1 kilobyte and 37. So if you remember, the classic McEliece requires keys of 260 kilobytes. You see that these keys are very, very compact. However, this is a very big however. First of all, the extrapolation technique requires very intensive simulations here. So it is not something that, I mean, designing your scheme may take a very long time. Furthermore, and this is more important, we don't know where the floor happens. So it may happen that the floor is too high, so that your extrapolated point is not valid. So we don't have a confirmation about the validity of this procedure. And this is still an open question. Okay, so at the moment, we don't know whether we can trust the DFI extrapolation or not. And consider that this is also probably a very promising line of research because saying something about this topic may be very important. For instance, if you are able to prove that some decoder has some DFR, then you are able to provide a decoder with no additional assumptions and formally proven DFR. So I think that at the moment this is one of the most important lines of research. Okay, so I think I am running almost out of time. I guess I have kind of 10 minutes. And I would also like to tell you something about the code-based signatures, because we have seen that for encryption schemes, we have pretty good solutions. We have conservative solutions, such as the classic McEliece, and we have more modern solutions that have some drawbacks. What about signatures? Well, we know, first of all, that classical signatures will be broken as well. So forget about DSA and RSA. We know that code-based we can say solution, in the sense that all the proposals that we have either been broken or have some drawbacks. For instance, if we consider the classical historic proposals such as KKS and CFS, they have drawbacks. I think I'm gonna skip this slide. No, in any case, there is an intrinsic difficulty in building a code-based signature because the classical trapdoor is hard to be constructed, since basically what we can do is that we start from a message M, we hash the message into a signature, and then we try to decode the syndrome. So we try to search for a vector having low weight. However, it can be shown that for parameters that have a practical interest, the number of possible syndromes is way larger than that of decodable errors. So that in the end, the probability to pick a syndrome that can be decoded is extremely small. If we want to increase this probability, then we are going to need extreme parameters, but the result will be that the scheme will be unpractical, because we are going to have a very large public keys. Okay, I will leave you the slide, so if you want, you can check these computations. So we have seen some proposals. I already told you about the KKS, the CFS. We have also had a scheme proposed by Baldi and other people. However, all of these schemes have seen some issues. some cryptanalysis, very large public keys. So no scheme is in the end good. One may think that since we know that lattices and codes have a lot of analogies, we may start from the very satisfying approach of Lubachevsky and try to apply it to the case of codes. There have been attempts in doing this, for instance, due to Persichetti, Song, and Lee. However, all of these solutions have been cryptanalyzed. So again, using Lubachevsky with codes is probably not a good idea. In particular, it can be seen that the problem lies within the nature of the scheme, because the functioning of Lubachevsky is not proper to be adapted to the case of ME metric. So that again, Lubachevsky plus linear codes in the ME metric is not a good idea. Okay, so okay, constructing signatures from codes is hard, but it's not impossible. Indeed, we have some solutions. For instance, we have Wave and Durandal, which are based on different approaches. So we consider the rank metric, or we consider the Hamming metric, but we search for vectors with very high weight. So there is something that works. Or we can do something completely different. That is, we start from an ID scheme, an identification scheme, which we transform using Fiat-Shamir. So if we construct signatures from identification schemes, we have some good aspects. For instance, we have no trapdoor, and we have small public keys. But however, normally the signatures are large. However, I think that this type of solutions is probably the most promising one, because of some aspects which I will try to explain. So let me spend a few words about this type of signature algorithms. Okay, so first of all, an ID scheme is a protocol in which a prover wants to prove his identity to a verifier. To do this, the verifier challenges the prover with random messages, and the prover has to reply to the challenge. So the protocol you see in the slide is the representation of one single round. However, what happens is that an adversary can always cheat with some probability, which we can call delta. So if we want to reduce the cheating probability, then we have to repeat the protocol for n rounds. Okay, when we use Fiat-Shamir, then the role of the verifier is replaced by an hash function, and we have that the number of the signature size is given by the number of messages that are exchanged between the two parties. So if we have to repeat the round, then we have a lot of messages, and the signature becomes larger. In particular, along the years, several ID schemes have been proposed. So, for instance, we have the classical ones that are based on binary SDP with low weight. We have the CV, which is based on SDP over non-binary codes. We have also a scheme that is based on the rank metric with low weight. And we have also a new scheme called LESS, which is based on the code equivalence problem, which is a completely different problem because it is not a decoding problem. So we have not, we don't have to decode anything. And also we have also different solutions, but however, they have not been peer-reviewed yet, so I have not put them in the slide. In any case, if we in this table, I have put a Nike level comparison between all the schemes we have at the moment. If we look at these numbers, we see that there is no breakthrough scheme, meaning that there is no scheme that is the better in any possible scenario. For instance, if we need something with a very small public key, then ID schemes are probably the best solutions, because you see that the public keys are really, really small. If we need something with very small signatures, then ID schemes are not the best thing. And we can rely on different solutions, such as Wave or Durandal, but we have to accept rather large public keys. We have schemes such as LESS that offer several types of trade-off. For instance, we can have very large public keys and small signatures, or we can reduce the public key by increasing the signature size. So in the end, at the moment, we have solutions, but there is no best something like the best solution. So choosing a signature scheme really depends on the type of application that you are considering. Also, having a look at the NIST competition, this is a very recent news, but NIST decided that they want to do an additional round since they are interested in new digital signature schemes. Indeed, at the moment, NIST is going to standardize a lattice-based signature, but they want an alternative, because lattice-based cryptography can be considered to be too modern in some sense. So NIST wants to find a backup plan, which is why at the conclusion of the third round, NIST will issue a new call for proposals, aiming to receive digital signature schemes. So in the end, the message is that if you are interested in crypto, you should keep an eye on the competition, because probably very new solutions with interesting aspects are going to happen. So this means that there will be a lot of work for us, and this may be good or bad. It depends on what you are considering. But I am pretty sure that in the future, we are going to see new proposals, new candidates, new implementation results. So things will be pretty interesting. Okay, so this is the last slide of my very long talk. I spoke to you about code-based cryptography, and I try to convince you that code-based cryptography is among the most studied and well understood schemes that we have nowadays. For what concerns encryption schemes, we have solutions that are essentially ready to be standardized, and these solutions are pretty secure, but they have some drawbacks. Maybe they are too conservative. Then we can aim to use more competitive solutions, such as those using QCLDPC and QCLDPC codes. But however, these schemes have the so-called DFR problem. So the researchers are trying to solve these issues. But again, the situation for encryption schemes is really good. When it comes to signatures, then the panorama is less satisfying because we have some intrinsic limitations. So at the moment, we don't have a perfect scheme. However, new solutions are appearing, also because of the upcoming call for proposals. So in the end, stay tuned, because my feeling is that some interesting things are about to happen. So that the panorama will probably change in the upcoming years. Okay, that's all. Thank you very much for your attention.